Welcome to G Fun Facts Online. Today we are diving straight into a technological revolution happening right now in 2026. Imagine a computer that calculates not with electrical currents, but with the fundamental particles of light. A machine tapping into the bizarre, counterintuitive laws of quantum mechanics to solve problems in seconds that would take today's most powerful classical supercomputers millennia to crack. This is the fast-approaching reality of photonic quantum computing. The global quantum computing race has fundamentally shifted gears. Early headlines were dominated by superconducting circuits housed in colossal, chandelier-like dilution refrigerators. But a new champion has emerged from the glowing world of optics. Photonic quantum computing, which uses photons to process, route, and store data, is revolutionizing how we think about scaling quantum power. It offers a viable, accelerated pathway to millions of qubits, room temperature processing, and seamless integration with existing global fiber-optic networks. To understand why light is poised to win the quantum race, we have to look at the physics. For decades, the standard approach to building a quantum computer relied on superconducting qubits or trapped ions. While they achieved remarkable milestones, they faced immense physical hurdles. Superconducting qubits are notoriously fragile. The slightest temperature fluctuation or stray electromagnetic field can cause what physicists call decoherence, collapsing the delicate quantum state and destroying the calculation. To prevent this, those systems require extreme cryogenic cooling, operating at temperatures colder than deep space, just fractions of a degree above absolute zero. As you add more qubits to scale up the computer's power, the cooling requirements and complex wiring become an absolute engineering nightmare. Enter the photon. Photons are the elementary particles of light. They have no mass, they travel at the universe's ultimate speed limit, and most importantly, they barely interact with their environment. In the realm of quantum computing, this aloofness is their greatest superpower. Because photons do not readily interact with each other or with stray magnetic fields, they are incredibly resistant to decoherence. A photon can carry delicate quantum information, encoded in its polarization, its path, or its arrival time, across vast distances without losing its quantum state. Crucially, the actual processing of photonic qubits can occur at room temperature. The complex waveguides, beam splitters, and phase shifters that make up a photonic quantum chip do not need to be buried inside a $1,000,000 cryogenic freezer. The computational core itself can just sit on a standard server rack. Because our modern telecommunications infrastructure is already built on fiber-optic cables, photonic quantum computers are inherently network-ready. Transferring a quantum state from one machine to another in a different city is an organic extension of the technology, laying the foundational bedrock for the future quantum internet. Building a quantum computer out of light requires three fundamental pillars: generation, manipulation, and detection. You cannot use a standard light bulb or even a traditional laser to run a quantum computer. You need highly specialized components that generate single photons on demand or specialized squeezed states of light. One leading method uses artificial atoms or semiconductor quantum dots. When excited by a laser, these nanoscale structures emit exactly one photon at a time. Another approach, known as spontaneous parametric downconversion, fires a high-energy laser into a specialized crystal, occasionally splitting a single high-energy photon into two entangled lower-energy photons. Today's industry leaders have refined these sources to fire billions of times per second with astonishing accuracy. Once generated, the photons must be manipulated to perform logical operations, known as quantum gates. This is achieved using silicon photonics, a technology originally developed for high-speed internet routing. The photons travel through microscopic tunnels etched into silicon chips called waveguides. By placing two waveguides incredibly close together, engineers create a beam splitter, allowing a photon's wave function to split and travel down two paths simultaneously, creating a quantum superposition. Phase shifters slightly alter the speed of light in a specific waveguide using heat or electrical fields, allowing engineers to manipulate the interference patterns of the photons to execute complex algorithms. After the light navigates the labyrinth of the quantum chip, the final state must be measured to extract the answer. This brings us to the detectors. Superconducting nanowire single-photon detectors are microscopic wires cooled to cryogenic temperatures, so they have zero electrical resistance. When a single photon strikes the nanowire, it breaks the superconductivity for a fraction of a nanosecond, creating a tiny electrical pulse. This pulse is the final classical output, the answer to the quantum equation. So while the detectors still require cooling, the massive computational core does not. If you follow traditional quantum computing, you might know the circuit model, where qubits sit stationary while logic gates are applied. But photons refuse to sit still. They are always moving at the speed of light. To solve this, photonic quantum computing uses a revolutionary architecture called measurement-based quantum computing. The computation does not start by feeding data into a blank slate of qubits. Instead, the machine first generates a massive, highly entangled web of photons called a cluster state. This cluster state acts as a universal canvas. The computation is performed solely by measuring the photons in a very specific, adaptive sequence. Because measuring a quantum particle destroys its superposition, the act of measurement itself sculpts the remaining entangled web, steering the quantum information through the logic of the algorithm. It is exactly like taking a solid block of marble, which is the cluster state, and using a chisel, which represents the measurements, to carve out the specific algorithm you need. By early 2026, the theoretical elegance of this technology has transitioned into hardcore industrial engineering, dominated by three major juggernauts. First is PsiQuantum, based in Silicon Valley. They have adopted an all-or-nothing strategy, bypassing small, noisy prototypes to aim straight for utility-scale, fault-tolerant quantum computing with over 1 million physical qubits. The industry rallied behind this in late 2025 when PsiQuantum raised a staggering $1 billion in Series E funding, led by BlackRock, Bailey Gifford, and Temasek, pushing their valuation to $7 billion. This war chest is funding the world's first utility-scale quantum computing sites in Brisbane, Australia, and Chicago. To handle system stabilization, they partnered with Linde Engineering to deliver one of the largest bespoke cryogenic plants ever designed for quantum technology detectors. PsiQuantum leverages existing Tier 1 semiconductor foundries to manufacture proprietary quantum photonic chips and high-performance barium titanate optical switches by the millions. In February 2026, they appointed computing veteran Victor Peng, former president of AMD, as interim CEO. On the software side, they partnered with Airbus to tackle computational fluid dynamics using their Construct software suite. They are developing fault-tolerant quantum algorithms to simulate non-trivial incompressible fluid flows over aircraft wings, potentially allowing Airbus to design radically efficient planes without relying on physical wind tunnels. Next is Canada's Xanadu. Instead of single photons, Xanadu uses squeezed states of light, a continuous variable approach, encoding more information into the amplitude and phase of the light waves. Xanadu recently announced a business combination agreement with Crane Harbor Acquisition Corp. To trade publicly on the Nasdaq and Toronto Stock Exchange with a $500 million capitalization. In June 2025, they demonstrated the first-ever Gotsman-Kitaev Prescale, or GKP qubits, on an integrated photonic chip. GKP qubits possess built-in error resistance, inherently correcting for tiny shifts and noise. To manufacture these, Xanadu expanded its collaboration with Tower Semiconductor in February 2026, co-engineering a high-volume production flow for a custom ultra-low-loss silicon nitride material stack. Xanadu is also solving immediate industrial problems, partnering with Mitsubishi Chemical to simulate radiation-induced blurring in extreme ultraviolet lithography for next-generation classical microchip manufacturing. Xanadu also dominates the software stack with Penny Lane, their open-source framework for quantum machine learning, which they recently integrated with the Munich Quantum Toolkit. Finally, we look across the Atlantic to France's Quandela, Europe's photonic unicorn. Spun off from the Center for Nanoscience and Nanotechnology in Paris, Quandela uses a discrete variable approach with semiconductor artificial atoms. In 2025, they launched Balenos, a 12-qubit photonic quantum computer delivering 4,000 times more computing power than their previous generation. They delivered a customized system named Lucy to the French Alternative Energies and Atomic Energy Commission, integrating it with the Joliot-Curie supercomputer. In February 2025, Quandela shocked the industry by reducing the required components for fault-tolerant calculations by a factor of 100,000, optimizing how their emitters generate entangled states to dramatically shrink the physical footprint. They are heavily focused on artificial intelligence, partnering with the Mila AI Institute in Quebec to develop hybrid quantum machine learning models, aiming to train neural networks far more efficiently than classical GPUs. This aggressive scaling earned Quandela the DIGITALEUROPE Future Unicorn Award in February 2026. Despite these successes, the photonic approach has unique engineering nightmares, primarily photon loss. Every time a photon passes through a beam splitter or turns a corner, there is a tiny probability it will be absorbed or scattered. In a circuit requiring thousands of sequential operations, losing photons means losing the calculation. Companies are combating this by engineering ultra-low-loss materials like silicon nitride and lithium niobate. Error correction is also being uniquely adapted for light through multiplexing. Engineers fire dozens of photon sources simultaneously. If one fails, optical switches instantly route a successful photon from an adjacent source into the circuit. Combined with advanced codes like Xanadu's GKP qubits, the industry is rapidly transitioning from noisy intermediate-scale devices to true fault-tolerant quantum computing. As utility-scale systems come online between 2028 and 2030, real-world applications will trigger massive paradigm shifts. In aerospace, fault-tolerant systems will perfectly simulate turbulence, slashing fuel consumption and global carbon emissions. In pharmaceuticals, simulating complex protein folding and drug binding will slash research and development timelines from decades down to months. The intersection of quantum computing and artificial intelligence could vastly accelerate the training of large language models, while drastically reducing the catastrophic energy consumption of massive GPU server farms. In cybersecurity, these computers naturally interface with fiber optics. Startups like IONQ, working with the US Air Force, have demonstrated converting quantum signals to telecommunication wavelengths, laying the groundwork for the quantum internet and absolutely unbreakable encryption protocols. The economic horizon is massive. The global photonic quantum computing market is experiencing remarkable growth, projected to reach $1.1 billion by 2030 and over $7 billion by 2036. Governments and multinational corporations realize this is a critical pillar of national security and economic sovereignty. Operating at room temperature, leveraging existing telecommunications infrastructure, and utilizing legacy CMOS foundries positions photonics as the most scalable, cost-effective quantum modality. For half a century, silicon-based classical computing has shaped human progress. But as Moore's law slows and our demands skyrocket, we need a new paradigm. Photonic quantum computing is answering that call. By harnessing the ethereal, frictionless properties of light, we are bypassing the limitations of older models. With PsiQuantum, Xanadu, and Quandela achieving unprecedented milestones, the timeline for quantum utility is accelerating faster than predicted. We are no longer just dreaming of a quantum future. We are actively carving it out of silicon, illuminating the path forward with the power of light. The age of photonic quantum computing is here, and it is set to change the world. Thank you for listening to G Fun Facts Online. Keep exploring the incredible universe of technology with us.